Hello and welcome to the last lecture of this lecture series. This lecture is on CAD tools for low power. We know that aggressive CMOS device size scaling has allowed realization of incredibly rich functionality on a small inexpensive die. So, as the device size has reduced, you are able to put more and more transistors on a chip. So, that has increased the packaging density and increased the power, and this has led to many challenges, as we shall see. And present day deep submicron technology not only has increased the speed, but also increased both dynamic and static power dissipations. As you have seen, because of the increase of a large number of transistors, the dynamic power has increased per unit area of the chip, and static power dissipation has also increased. So, in this scenario, failure to meet power goals can have costly consequences on the viability of an IC and overall system. So, power has become a very important parameter, as I have emphasized on many occasions. Now, question naturally arises, can you do low power synthesis design of ICs incorporating low power techniques manually, because the number of transistors is very large, IC is very complex, you want to incorporate many complex functionality on a chip. Can it be done manually? The answer is no. So, traditionally use of RTL synthesis has led to major improvement in productivity. All of you are maybe familiar with RTL coding, writing programs in Verilog or VHDL. So, what there you write your system level functionality with the help of Verilog or VHDL. However, this has introduced a major disconnect between the front end design and the real circuit which burns power. So, who is writing program in Verilog, to him it is no longer a circuit or a net list of electronic components, but a high level functional description software in Verilog or VHDL. So, this has introduced a major disconnect between the actual circuit and the way the design starts. So, RTL synthesis is traditionally timing driven with several iterations to optimize area and fix timing violations. So, that is the basic approach that is followed in RTL synthesis. So, power was not a real concern until recently. Unfortunately, what has happened, designing for low power is now a necessity rather than a choice. So, as you incorporate low power functionality, low power features, low power tools and low power techniques in your design, the complexity increases. So, in spite of this, you have to incorporate them. So, what is the alternative? Okay, let us first look at the limitations of RTL coding and its applicability to power reductions. What really you can do using RTL coding, that means using Verilog or VHDL. Unfortunately, in RTL coding there is no provision to use multi-FET, multiple VDD, body biasing and power gating. And obviously, since these cannot be done, you cannot use any technique that will reduce the static power. So, no static power reduction technique can be implemented with the help of traditional Verilog or VHDL coding. And as the supply voltage and operating frequency are not handled in RTL level, that means you cannot really realize circuit with multiple supply voltages. So, you cannot really incorporate multiple VDD design. Here they are logic level one means it can be 5 volt, it can be 1 volt even if you use multiple VDD in your circuit. So, that is a serious limitation. So, the dynamic power reduction cannot be carried out by supply voltage scaling. However, the dynamic power can be reduced primarily by reducing the switching activity alpha. So, there are some techniques which can be implemented, and these techniques will primarily reduce the switching activity, and commonly used techniques in RTL synthesis to reduce alpha, that switching activity, are bus encoding, clock gating, FSM state assignment. I have already discussed in detail about these techniques, and using these techniques you can reduce the transition activity or switching activity to reduce dynamic power, but you cannot go beyond this. However, we have already discussed in detail various techniques, advanced techniques for low power, and these are some of the benefits, and here some of the important techniques are mentioned. Number one is clock gating. Clock gating can be used when some parts of the circuits are not in use in when the circuit is in action. When the circuit is in operation, it can be in the block level or it can be in the gate level, we have discussed in detail. So, you can incorporate clock gating, and we have seen clock gating can reduce gives you large dynamic power benefit, but very small static power benefit, because using clock gating you are essentially reducing the activity of the circuit. So, that does not reduce the static power dissipation, and it has very small impact on the design, because the RTL coding has to be modified little bit to incorporate clock gating, and also it has got small impact on verification, and also very small impact on implementation. So, traditional approach can be followed with small changes. Similarly, you can incorporate multiple VDD circuits when different parts of the circuit can operate with different supply voltages. Again, this can be done in the module level or gate level. So, in all these cases there is possibility of reducing the dynamic power. So, in this case also there is large benefit on dynamic power, reduction in dynamic power take place with small reduction in static power, and it has little impact on design, because multiple circuits can be realized. Essentially only requirement is here that some parts of the circuit you have to take power rail of different supply voltages, and it has got low verification impact, and that means whenever you go for verification it has low impact, and implementation impact is medium. However, whenever you go for dynamic voltage and frequency scaling, this can be done in applications where the circuit can operate, has different the circuit or the system will require different performance level. That means, the sometimes you look at 10% performance, sometimes you require 20% performance requirement, and so on. In such a case, you can use dynamic voltage and frequency scaling, and again this has got small large impact on dynamic power, small impact on static power, and design impact is medium, because you have to modify some parts of the circuit, you have to incorporate that variable voltage supply, you have to incorporate variable frequency circuit, and it has very strong impact on verification, because it is very invasive, and medium impact on implementation. That means, the implementation becomes little complex. Then the first three techniques are commonly used, are traditionally used to reduce dynamic power. Then to reduce static power, you can use multiple threshold voltage circuits with small impact on dynamic power. It does not give you much reduction in dynamic power, but it gives you large reduction in static power, and whenever you go for multi-VDD circuits, it has medium impact on design and small impact on verification, and medium impact on implementation. Then power gating. which is very important in our present day design. It has again a small impact on dynamic power, because it leads to very small reduction in dynamic power, but it leads to very large reduction in static power, and it has medium impact on design, large impact on verification. It is highly invasive that we have seen, and it has got medium impact on implementation. And these techniques can dramatically reduce power consumption in deep submicron techniques, deep submicron circuits. However, these techniques traditionally require ad hoc, time consuming, risk prone and manual verification implementation approach, unless automated using CAD tools. That means, unless you implement these techniques using automated CAD tools, these are not really very beneficial in the sense, because it takes long time, they are risk prone, and manual verification implementation is not a very good situation whenever you have got large, complexity is very high. So, what is the how the low power techniques can be automated? One approach is overlay power intent on top of the design. That means, what you can do, you can overlay power intent on top of the design. So, on top of the traditional design approach, you will overlay power intent. How it can be done, that I shall discuss, and in each step of the flow to use power intent and take into consideration the following issues. As we know, there are various issues related to low power techniques, such as power domains whenever you are using multiple VDD, then power distribution network, clock tree network, then power state, they will have different voltage, different states, then you have to use level shifters, you have to use isolation circuits, you have to use retention hardware, and also you have to take into consideration the switching activity at different parts of the circuit. So, these are the various issues you have to take into consideration whenever you go for using low power techniques. UPF Accellera has proposed a unified power format, which has been widely accepted by industry, and it provides the ability for electronic systems to be designed with power as the key consideration early in the design process, maybe at the RTL level. So, it accomplishes this through the ability to allow specification of implementation related power information early in the design process. That means, whenever you are doing RTL synthesis using Verilog or VHDL, along with that you will also incorporate your low power intent with the help of UPF. So, UPF provides a consistent format to specify power aware design information, which cannot be specified by HDL code. As I have told, HDL has got serious limitation, and it cannot really incorporate most of the low power features that I have discussed, or it can be used when it is undesirable to directly specify within the HDL logic, as doing so would tie the logic specification directly to a constant power implementation. So, in both these cases it is necessary, it will be the power intent will be specified with the help of UPF. So, this is actually not only UPF, there are two well known power formats. One is UPF, that is your unified power format, developed by Accellera, and it has been accepted by many standards. Another is common power format, because unified power format or UPF is most popular. I shall be primarily discussing based on UPF. And as you can see, UPF defines consistent semantics across verification and implementation, and that means what is implemented is the same as that of verified. So, you can see it can be used throughout the throughout all the design steps like synthesis, placement and routing, and you will be doing simulation, you will be doing verification, and also you will be performing sign off, as we shall see. So, UPF along with your VHDL coding or RTL coding can be used throughout the synthesis cycle, starting from system level to the layout level. So, here is the design flow. So, what you have to do, define power domains and logical power intent using UPF. So, that is essentially the definition stage. Then you will do simulation, various low power, I mean after incorporating those low power techniques, power up down behavior and multi voltage static rule checking. So, we will do simulation and do verification. Then top down multi voltage, multi supply, multi voltage synthesis. So, that means you will perform synthesis after verification, and in this case as you can see the IC can have multiple voltage, multi supply, that means you will be using different switching, then multiple threshold voltages in the synthesis, and physical level implementation where you will implement power switch planning, power network implementation with voltage areas. So, this will do physical implementation, then power aware placement, clock gating, clock tree synthesis and routing. So, these parts we will do implement synthesis, and then you have to take into consideration multi scenario. So, multi corner, multi mode scenario, that means you have to take into consideration all possible alternatives, that means the low voltage, high VT, low VT and so on. Then finally, you will be performing sign off and realize the low power device, where you will do low power formal and rule checking, where you will check whether your design and actual implementation are same or not, and also will do power analysis. Obviously, you will require various tools to go through this low power design flow, and CAD tools are available for these purposes from various sources: Synopsys, Cadence, Sequence Design, Atrenta and Magma. So, all of them have developed low power CAD tools, and they provide, of course, their functionality may differ little bit, but they will provide some of the features which I have already mentioned. We shall primarily focus on Synopsys CAD tool, Synopsys tool and low power solution. So, this is the roadmap of Synopsys, and the Synopsys predicted that this is how industry will adopt various techniques of low power techniques. As you can see, those who are trailing, they will be using simple single supply voltage, single VT circuits, but the industries which will be in the mainstream, they will be using multi voltage, and they will be using clock gating, and those will be using little advanced techniques. Gradually, as you move from 2008 to 2009, they will be gradually that empty CMOS based power gating will be adopted by most of the industries, and then multi voltage and power gating will become commonplace, or will become commonplace in 2009 along with body biasing. And then beyond this, you have got industries which will be using cutting edge technologies. They will use adaptive voltage and frequency scaling and that means they will be not only using multiple voltages, multiple threshold voltages, but dynamic voltage and frequency scaling. So, this is the roadmap that was predicted by Synopsys, and various industries are in different stages of this. The CAD tool that has been proposed by Synopsys is known as Eclypse. So, it is a comprehensive approach, power aware tools at all levels of design hierarchy, starting from early architectural and system level analysis to verification, then RTL synthesis, test, physical implementation, and then finally sign off. So, as you can see, it is not really a single tool, but say suite of tools starting from design intent to sign off. So, various tools are developed which are part of Eclypse, which I shall discuss their various functionalities one after another, and this Eclypse supports the Accellera unified power format, that is UPF that I mentioned, which is an open industry standard to specify power intent. And this is backed by low power methodology manual. I have mentioned about that low power methodology manual that has been developed jointly by Synopsys and ARM together, and the various approaches which are proposed in this low power methodology manual have been adopted in Eclypse. First, we shall focus on innovator. Innovator it provides a virtual platform at architectural and system level. What do we really mean by virtual platform? So, it gives you simulation models of all components that you require in implementing a system on chip, that means processors, coprocessor, buses and various other components that you require are provided in this, and these virtual platforms are simulated models or all the components of the SoC as I mentioned, and then at the design phase it can calculate dynamic power on the fly. That means, you have got the simulation models, and using that simulated models you can run some application program, and as you run some application program on the fly, it can give you information about the dynamic power consumption, and based on that you can that means the plot of dynamic power can be correlated against software activity. So, these are the key features of this this innovator, and that means it gives you architectural level power analysis, it can model power consumption, it can identify peak powers. So, what it really do, how it will help you at the design step, you will be doing I have already discussed about hardware software partitioning or hardware software code trade off. That means, same functionality you can implement by hardware or by software or by a judicious combination of hardware and software. So, in this design phase, this software, this innovator helps you to plan that. That means, as you do the simulation, you can identify which part to implement by software or how you can really do the partitioning such that your power budget is not violated. So, that can be done in the early design step. So, it is a hardware software co-verification and early power analysis. So, this is a very useful tool at the design step, and not only that, it provides you various designer IP, various IPs which have been developed by many industries. Those are also available and they can be simulated with the help of this innovator. Okay. And then after the early design is done and you have identified necessary hardware and software to be implemented, normally VCS is commonly used for the purpose of RTL and netlist simulation. So, this with the help of this RTL and netlist simulation tool, you can do compilation, then you can do simulation, and you can find out the functionality of the circuit. But unfortunately, this VCS cannot take the power intent information in the design. So, what can be done? You can incorporate MVSIM with VCS. So, MVSIM with VCS can be done, because MVSIM is a co-simulator that works with VCS through Verilog procedural interface programming language interface. So, Verilog procedural interface programming language interface, with that it can work together. So, it is a co-simulator, and as you can see, just like VCS can accept the RTL or so that that logic level netlist. The VCM MVSIM also can accept the same RTL or the logic level netlist. It can accept the same test bench as the VCS, and of course, they interact with VPI as I have already mentioned. And then it can, that means in the additional thing that the MVSIM does, it accepts the power intent specified by UPF. So, UPF specifies those multiple voltage domains, multiple VDD circuits and so on. So, that means the low power intent part is the additional thing that MVSIM accepts. So, it can completely verify voltage control techniques such as dynamic voltage and frequency scaling, low VDD standby, and it can detect bugs when the multiple voltage translation occur in the design. So, so far as the VCS is concerned, it does not really differentiate between two voltage levels. That means, suppose you are using a circuit with, say you have got a circuit which is operating at say 0.8 volt, and here another circuit which is operating at maybe another part of the circuit or module operating at 1.2 volt. So, if a signal goes from here to from this voltage domain to this voltage domain, VCS say voltage level is 1. So, VCS will take a signal level 1, that means a 0.8 volt is going to another voltage domain, and that is also considered as voltage level 1. But as you know, we know the consequences of this. So, when a low voltage signal I mean a high voltage signal goes, high level signal goes from a low voltage domain to a high voltage domain, it can lead to that short circuit power dissipation or crowbar power dissipation, but unfortunately VCS cannot differentiate between the two voltage levels. On the other hand, this MVSIM, whenever you use MVSIM along with VCS, then this voltage differences are identified, can be identified, and actually MVSIM is truly voltage aware. So, the various voltages it can take care of. So, it detects bugs when multiple voltage transitions occur in the design. So, this is how you can do the simulation, and after the simulation you will be doing verification. So, MVRC is the tool that is used for static voltage aware verification. So, as you can see, with the help of MVRC, it validates power intent across design flow. So, RTL along with UPF, you are giving your specification, and MVRC will accept that, and you can see it will do not only the design, and as you do the synthesis and net list is generated, MVRC will do the net list, it will do the necessary verification, and as you do the placement and routing implementation, that also is verified with the help of MVRC. That means, it will do functional checks, it will do net list handoff, it will do final sign off. So, it is a static voltage aware verification tool. So, it is MVRC is able to perform checks on power intent consistency, and can also validate that global control signals do not originate in inactive power domains and end up driving logic in active power domains. We have seen in a circuit, some parts will be in standby, some parts will be in active state. So, no signal should go from a standby part of the circuit to the active part of the circuit. So, this detection is done and verification is done with the help of MVRC. So, MVRC, not only MVRC does all these things, it can ascertain the correct insertion and connection of level shifters. We have seen you will require level converters whenever you are using, will be using multiple voltage domains. So, it will ascertain the correct insertion and connection of level shifters, isolation cells, power switches, retention cells, and always on elements. That means, various components that is required in the context of multi VDD circuits, or whenever you incorporate those power gating techniques, those components whether they are correctly inserted or not, that can be verified with the help of MVRC. and as you can see, MVSIM and MVRC together is performing. So, this MVSIM performs multi-voltage simulation, and MVSIM performs multi-voltage simulation, and MVRC performs multi-voltage static checking, static rule checking. So, that means MVSIM performs voltage aware simulation that verifies power states, transition and sequences, and MVRC performs voltage aware static checks that verify actual power implementation versus intent. That means, whatever is the intent and actual implementation, by comparing that, it can check whether it has been implemented correctly or not. So, what is the net outcome? You can see you start a design, and this using this MVSIM and MVRC, what is happening, verification and debug of firmware for power management is done with the help of this in a single step. So, before you commit it to silicon and eliminate respins, that means normally what happens, you do the implementation, if it does not satisfy the purpose, you have to again go back to the design. So, that can be avoided, and that will reduce the time to market of a particular chip or device, and you can tape out very quickly. Okay. And this is that multi-voltage verification flow that is done with the help of MVRC and MVSIM. First, there is a multi-voltage compiler MVSIM CMP that compiles Verilog RTL files and UPF. So, you can see here always you are incorporating these two together, VHDL or Verilog code along with UPF power intent file. So, it compiles this multi-voltage compiler will do the compilation, and it will report syntax and semantics error. So, the syntax and semantics checking is done with the help of this compiler. Then multi-voltage database generator will generate some information. It reads binary design view created by MVCMP and elaborates design and creates multi-voltage database. So, it will generate a database which will be used by MVRC and MVSIM, and this database is used by MVSIM and MVRC. So, you can see the flow here. So, it goes through MVCMP and it checks the syntax and semantics, then the database is generated, that goes to this MVRC and MVSIM. So, this MVRC does structural and power architectural checks on designs with those vectors, and multi-voltage simulator MVSIM, as I have already mentioned, it co-simulates with VCS to do voltage aware functional simulation. So, this is the database is used by MVSIM and MVRC. So, this is the design flow for simulation and verification. Now, after the simulation and verification, as I mentioned, you have to do the design. So, this is in the design implementation phase, you have to perform low power optimization including synthesis and placement and routing. So, that means and all the synthesis that will incorporate low power techniques, and you have to perform placement and routing of various components of that means switches, clock gating circuits and other things, and not only that, you have to take into account design for test. So, present nowadays design for test incorporation is very important. That means, you will incorporate some hardware as part of the chip which will help you to do the testing. So, you will do this design which will be used for the purpose of testing at later stage. So, you have to incorporate that. So, this power aware synthesis tool should carefully balance area, timing and power constants. So, not only area is important or timing is important, power constants are also very important. All these three are to be properly balanced with the help of this design implementation tools. What is done in this Synopsys tool? They have used design compiler enabled by power compiler. So, the power compiler is the addition which will take care of these those power intent implementation things. That means whatever you that low power techniques that we implement, that will be taken care of with the help of this power compiler. So, design compiler enabled by power compiler is the solution, and it uses physically aware algorithms and techniques to assure consistent high correlation between synthesis and place and route. So, we shall see how this high correlation is obtained between synthesis and place and route. So, as I mentioned, design compiler enabled by power compiler is done. Here question arises, how many power switches are to be used? We are interested in reducing the number of switches, because if you add more number of switches, that will increase the area, and on the other hand, if you increase lesser number of switches, that may lead to voltage droop as you draw larger current. So, here is a trade off between performance and area. So, then the not only how many switches, how do you put them, where do you place them? That means too few switches cause IR drop issues, voltage drop takes place, and too many switches take valuable cheap area, as I mentioned. So, what this design compiler enabled power compiler does, it generates several design options. So, design option A, option B, option C with various features. That means, they can have design different area, you can see different area, and also different and the different delay, different resistance and delay, and designer can choose has the choice of selecting one of the few such good designs. That means, this can this is how, depending on the application requirement, one can choose the best out of the best solutions. So, optimal power mesh design and analysis tool provides a means to quickly narrow down to the best solution from the possible alternatives, as I have mentioned. So, it typically reduces power from 5% to 20%, 20% plus, and implementation is automatically optimized. So, it various optimization is done. I shall discuss some of the optimization techniques that is being done. For example, it does power aware placement. So, if the placement is not done properly, it may lead to lot of power dissipation, and simply by placing them properly, the power dissipation can be reduced. So, this is how it is being done, and and you can see this is the low power placement after, and this is baseline placement before. So, using this tool you can achieve this power aware placement. As I mentioned, this this company's design compiler along with power compiler helps you to do that. Then coming to clock gating, we have seen clock gating are to be inserted, and if you can insert them automatically, there is nothing like it. And you can see traditionally you can use clock gating for two purposes. In the first case, as you can see, you can use it to reduce power dissipation. That means, if you use it early in the closer to the source of the clock. So, this clock gating has been done closer to the source of the clock tree, and it is driving the subsequent parts of the clock tree. If you can insert a clock gating here, it will lead to larger saving in power dissipation. On the other hand, this will introduce whenever you can this will introduce lot of clock skew through different parts of the circuit. On the other hand, you can introduce this clock gating close to the resistors. So, here you can see this is the clock tree, and these clock gating circuits have been incorporated, which are very close to the resistors. So, clock gating close to the resistors, this optimizes the clock skew. So, the delay of different paths, that is your clock skew, difference in delay of different paths, that is your clock skew. That clock skew can be optimized with the help of this technique. Now, using the automated CAD tool, what is being done, the clock gating is introduced judiciously in different paths. As you can see, it has incorporated clock gating circuits. One is close to the source, another is close to the registers, another is in between. So, by doing that, you can what it does, it optimizes clock skew, insertion delay, area, clock tree power and total power. That means, it is optimizing multiple parameters simultaneously, not only area, not only clock skew, not only delay and various parameters it is trying to incorporate optimize simultaneously, and that is being done with the help of this automated CAD tool. Okay. So, this is your clock tree generation, and what the power aware placement does, this IC compiler takes into account net switching activity along with timing and congestion to place cells such that the nets with high switching activity are short and are as short as possible while meeting timing and congestion criteria. So, you can see this is before, that means, here neither the switching activity nor the congestion has been taken into consideration, but here for example, this particular net has high switching activity. So, the length of this particular net has been reduced. So, it has shortened the high activity nets. So, this tool has reduced the length of this high activity net, and also it has this part for example, this particular clock tree is driving this register as well as this register, and these are wide apart. So, in this tool they have been clustered together to minimize clock tree power and area. So, clock tree power and area is minimized by clustering this part of the circuit. So, clustering the resistors. So, this power aware placement will definitely reduce various parameters that I have already told, particularly it will reduce the power dissipation due to switching activity, and also it will reduce area because it reduces the net length. Okay. So, this shows how the design compiler and IC compiler works together. I have mentioned that along with design compiler, you will be using IC compiler to do various optimization, placement, routing and all these optimizations. Essentially, it is a multi-corner, multi-mode optimization. So, concurrent MCMM aware synthesis, placement, routing and optimization transforms reduce turnaround time of complex designs. So, this multi-corner, multi-mode optimization will help you to get optimization, and also it will reduce the turnaround time of very complex design. On the right side, here there is a plot and it shows the correlation between the synthesis and layout. You can see here there are this plot shows and here the layout power and here the DC power. So, you can see at the design time what was the power and here is the layout power. So, you find that DC by IC compilation power correlation is very high. So, correlation is within 10%. So, this shows the efficacy of the tool. That means, the design and layout are very close and only 10% the correlation is within 10%. So, this shows the how good is the tool and how it helps to accurately does the placement and routing and various design techniques it performs. Okay. As I was mentioning about the testing. So, you have to incorporate design for testability. That means, you have to incorporate scan chains. I am not going into the details about the testing. There is a full course on testing and verification, where how to incorporate scan chains are discussed in detail. So, you have to incorporate scan chains which can be used for testing, and these are incorporated in the design. Not only you have to use them at the time of design, but at the time of actual testing with the help of ATPG those are automatic test program generation hardware that generates the test sequence. And at the time of testing, it has been found that at the time of testing lot of switching activity take place, and actually the switching activity may be higher than when they are actually used. The reason for that is, whenever you are testing with the help of ATPG, you may be simultaneously activating different parts of the circuit, and lot of dynamic power dissipation will take place. But in practice, whenever they are being used, they may not be used in parallel. So, what can happen, the power dissipation may be more at the time of testing, and this may lead to artificial failure of the chip. So, it may not fail when it is actually used, but it may fail at the time of testing. So, it is a kind of artificial failure. So, this that means this testing, at the testing time you have to develop techniques such that this artificial failures can be avoided. So, that is being what is done with the help of this tool. So, during actual testing with the help of ATPG, you can say this line is a user specified switching budget. That means, at the time of testing or use, it should not exceed this line. So, if you do not use the automated CAD the CAD tool that I mentioned, that is your DFT DFM using DFT Max Tetra Max. So, this tool actually identifies how you should really apply the test sequence such that the switching budget is not exceeded. So, this is the baseline ATPG, and you can see here it is exceeding the baseline the power budget switching the user specified switching budget, and this may lead to artificial failures. On the other hand, this part, the lower part of the circuit, you can see the power dissipation has reduced to around 10-20% compared to 60% with the help of this low power ATPG, which is provided by this tool. So, you can see at the time of actual testing, the power dissipation can be significantly reduced with the help of this tool. Okay. Coming to the last stage, that is your design sign off stage. So, whenever you are signing off, that means you are releasing the chip for commercial implementation. At this stage, you have to do certain things which are mentioned here. You have to perform in-depth analysis of the implemented design to verify that the functionality goals specified in the beginning with the help of UPF and VHDL or Verilog code are fulfilled or not. Then you have to compare the original RTL and UPF files with the final this is known as PG pin or power ground net PG pin netlist to verify that they are equivalent. That means, you have to perform verification with the intent with the actual implementation. That verification has to be done, and it can be done with the help of several tools known as Formality. So, MVRC does the consistency checks I have already discussed. It will do syntactic and semantic checks, and functionality checks, architectural checks and structural checks will be done by MVRC. I have already mentioned about that. And then power and ground checks, where it checks whether different parts of the circuits are getting the power supply or ground lines or not. This is also done with the help of MVRC. Then you have got Formality, which does the equivalence checking, and prime time suit, which does static timing analysis, and prime rail, which does full chip dynamic voltage drop and electromigration analysis. So, with the help of this the design sign up stage is performed. You can see this is the Formality, the equivalence checker. So, it takes the RTL as input and also the netlist, and it compares them. So, it is an equivalence checking solution using formal and static techniques to determine whether two versions of a design are functionally equivalent or not. So, it extends functional equivalence checking to include power effects on functionality. So, it is not only taking into consideration the functional behavior, but also the those power effects as you incorporate those low power techniques, and it identifies errors long before the final sign off. Okay. Then prime time suit enables full chip concurrent timing, signal integrity and power analysis in single correlated environment, and these are the various components of prime time suit: prime time SI, prime time PX and prime time VX. And the key features of these prime time suit is highly accurate composite concurrent current source, modeling of automatically scaled timing. It does signal integrity and power calculation based on IR drop and multi voltage condition, and sign off straightforward, sign off is straightforward and reliable with the help of this tool. So, this is how the prime rail does the rail analysis in detail. So, it can do that empty CMOS rush current whenever you are using empty CMOS based gating, and that's it checks whether there is any heavy current is flowing or not, and it does what if diagnosis. That means it can checks I mean what has failed and which parts where there is that large power dissipation. So, these are the various stages: parasitic extraction, power analysis and rail analysis, and it can perform it can identify voltage drop and electromigration. So, it is a full chip dynamic rail analysis tool that helps you to sign off. And this is the last slide that gives you the complete Synopsys low power design flow. So, you can see starting with functional verification, which can be done with MVSIM with MVRC, then the implementation, which can be done with the help of design compiler and power compiler and IC compiler. Complete design can be done along with low power intent. Then you can do equivalence checking with the help of formality at various levels of design hierarchy. Then finally, timing and power off you can do with the help of prime time power, prime time PX, prime time PX and power rail. So, that is also done at design at different levels of design hierarchy. So, this slide gives you a complete picture of the design flow and different tools which you can use in the for the low power synthesis of digital circuits. So, with this we have come to the end of not only today's lecture, but also end of this lecture series. Thank you.